The views expressed on Science for the People are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
This week on Science for the People, we're talking about meat minus the animal. We'll speak with scientist Dr. Mark Post about laboratory-cultured beef and its implications for food security, environmental impact, and animal welfare. Welcome to Science for the People. I'm Jessie Yaros. Today we're talking with Dr. Mark Post, chair of the Physiology Department at Maastricht University. His primary research is in tissue engineering for medical applications and for food, the latter of which he is here to talk with us about today. He presented the world's first lab-grown hamburger on live television in 2013, and since then has been working on improvements and scaling up of production of cultured meat. Mark, thanks so much for being with us today.
Welcome. Hi.
So, could you start with telling us how and why you got involved in such an interesting line of research?
Well, I'm a medical doctor and mostly a vascular biologist, so interested in blood vessels, and we ended up doing tissue engineering of blood vessels for bypass grafting. That technology is the same that we eventually used for muscle tissue engineering, and I ended up doing that by getting acquainted with that subject through a guy here in the Netherlands who was obsessed with this idea for about 30 years or so. And at some point he assembled a group of scientists from Utrecht, Amsterdam, and Eindhoven to start working on it with a grant from the Dutch government. Great.
And you continued to do the research after the grant had already ended, is that correct?
Right, that's correct. At the end of the project, we didn't have really a hamburger to speak of yet, but we did have the technology to make it happen, but didn't have the money anymore. So, and I thought it was just crazy because this was a great idea and we should be able to get funding for it. So we developed this idea of creating a sausage basically from a pig sample and present it to the public with the pig running around on the stage. But we still didn't have the money, but we did have a lot of publicity, and through sort of all sorts of, well, mostly through media contacts, we got the funding to do this. But it was American funding, so it became a hamburger instead of a sausage.
We do like our hamburgers here in the U.S.
Right.
Wonderful. So, I guess since it is a hamburger, could you take us through the steps, step by step, what it takes to grow a hamburger patty?
Well, we start with stem cells. Every mammal, or even birds and fish, have stem cells in their muscle. They're designated muscle stem cells. So they sit there doing nothing, just waiting until the muscle gets injured, and they repair the tissue by first dividing, multiplying, and then forming a new tissue. And that's exactly what we are doing. We take those stem cells out. We let them multiply in, let's say, a petri dish until you have trillions and trillions of cells. And then we put 1.5 million cells together in a small gel where the cells can find each other. They can form a muscle fiber. They start to contract in a petri dish, even if there's no reason for them to contract. They start to contract. They start to build up tension, and that tension is the biggest trigger for protein synthesis. So they're the contractile proteins that usually make the muscle contract, but are also sort of the nutritional value of meat for us.
Huh, interesting. Would you like to continue? I'm sorry.
Right. So then you have a muscle fiber consisting of 1.5 million cells. And what we basically did, we made 10,000 of these muscle fibers and kneaded them into a patty with breadcrumbs and egg white and salt and that sort of thing.
Okay. So you mentioned that I guess the building block is stem cell, and it's stem cells that have a fate of musculoskeletal cells. Is that... It's the only cell fate that's possible for them?
It's not the only one, but it's the predominant one. We just found out that they can also become fat cells, which for us is very fortunate because we also need some fat tissue in that hamburger eventually.
Okay. And that is really interesting because at least people always say the taste is in the fat.
Right.
So
that's not entirely true, but I guess we all can experience that if you have a very lean muscle, it's actually very difficult to distinguish from which animal it's coming. Until you have a piece of fat with it, then you immediately recognize it as a cow, pork, or lamb, for instance.
Oh, that's fascinating. Is it that the fat cells may be differentiated between species more so than the musculoskeletal cells?
Well, it could be. There are definitely differences between fat tissue that you take from a pig or from a cow. So yes, the composition is different. The cells are slightly different, and it may be that there are more differences between fat cells in general than between species than between muscle cells of different species.
That's really interesting. I guess one of the main questions I have is how long does it take from the beginning of this process, getting the sample of stem cells, to the ultimate hamburger?
It takes about 8 to 9 weeks. And it's interesting because it's an exponential process. Most of it is dependent on how fast the cells divide. And that is something that is just in mammalian cells is a fixed time. It takes about 24 to 30 hours for a cell to divide, and you don't want to really mess with that. You don't want to shorten that in any way. So, but they do divide, and then one cell becomes 2, and 2, 4, and 4, 8. So if it takes, let's say, 8 weeks to make one hamburger, it takes 8 weeks and 1 day to make 2 hamburgers. And 8 weeks and 2 days to make 4 hamburgers. So it's, if you have the capacity in your system to grow as many cells at the same time as you can get, then time is no longer sort of a limiting factor.
Okay. So you mentioned that you are basically layering a bunch of different meat fibers, beef fibers, on top of one another and mixing them with some other ingredients to make a burger. And originally the concept was for a sausage, which is also sort of ground beef product.
Right.
What is the likelihood of being able to use this technology to create a slab of meat, like a steak?
Right. Well, that requires a little bit of tweaking of the technology. So this, what we have been doing right now is allowing the cells to self-organize in a tissue. There is a limit in size, which is basically about 1 millimeter in diameter. And that has to do with diffusion limits of oxygen and nutrients that have to come from the outside and go all the way in. So if you want to make a steak, you have to do 3 things. One, you have to impose from the beginning a larger 3D structure on all these cells. So you start with a much larger number of cells and you impose one big, large 3D structure, for instance, through 3D printing. Then you need to have a channel system with where medium and with oxygen and nutrients can be perfused through the tissue, much the same way as we have blood vessels. We might want to use blood vessels for that. We are not quite sure, but we definitely need a channel system and a perfusion system. And third, because a slab of muscle is usually muscle fibers adjacent to fat cells and fat tissue growing together, you need to figure out how you can get the muscle cells and the fat cells growing together, although initially they need slightly different conditions to grow under. This is not something that is extremely difficult to do, but it is time consuming, and it will just require time and money, basically.
You mentioned 3D printing, and there is developing technology in how to 3D print meat, though I believe it's not as developed as your technology. Is that correct?
Right, that's correct. And again, 3D printing is not the only thing that you need to do. You need to also co-culture those cells and get a channel system like this in place. Right.
But 3D printing, you would say, is not necessarily a competitor to your technology. It might, in fact, be able to enhance what you can do?
Right. We will need a system like that. It doesn't necessarily need to be 3D printing, but some sort of larger free-form fabrication that allows you to impose a larger, bigger 3D structure on the cells.
Okay, I'd like to talk a bit more about what your lab has been focusing on in the last few years in terms of optimizing the cultured beef in terms of look, texture, taste, nutrition. Now, you've already mentioned a bit about fat and protein. Could you expand upon those factors a bit?
Right. When we presented the hamburger in 2013, it was a proof of concept, and we knew that the way we produced that was eventually not the way we're going to do it. So first of all, we used serum, which is a blood-derived product from animals, to grow the cells. And eventually you cannot continue doing that. So we found replacements for serum so that the cells can grow without serum, but with these replacements. That works reasonably well, and we're still sort of optimizing that. Second, you already mentioned the fat. We added fat tissue to the whole process so that we can now culture fat tissue from cow cells, and that to enhance taste and to enhance the mouthfeel. We improved the protein content, very specifically a protein called myoglobin, which gives meat its red color, but also its heme iron content, so it's a nutritional value, and probably also taste, some claim. And fourth, we changed the way of producing so that it can be scaled. So traditionally it's in petri dishes or in flasks because these cells need to grow on a surface, but eventually you cannot scale that. So we wanted to move to a larger bioreactor, a tank if you like, a stir tank. But because the cells have to grow on a surface, you need to grow them on microcarriers that are suspended in a tank like this. And that's what we have been working on in the last couple of months.
So what is the serum that you are now able to use made from?
It's mostly plant-derived, and some of the proteins that you need that are essential in serum that you require for that these cells require to grow are made from recombinant technology, so are made either in bacteria or yeast or algae.
So, for listeners who are unaware, the original media was fetal bovine serum, am I correct?
Right, exactly.
Which is used pretty often in research and growing of cell cultures, but can be controversial in such a publicized project, considering the way it's made from extracting blood from a live fetus's heart.
Well, that's one reason, but also since these are bovine fetuses, if the whole purpose of this endeavor is that we go from 1.5 billion cows on the planet to, let's say, 30,000, and then obviously we don't have supply of serum anymore. So it's for all sorts of reasons, animal welfare, sustainability, regulatory issues, diseases that may come with serum. There are all sorts of reasons to get rid of that serum, and that's why this is a big step forward and a big endeavor.
Oh, wonderful. In terms of the increase in fat cells, you mentioned that the stem cells can I imagine given the right conditions be I guess prompted into becoming fat cells. Is that how you added fat into the burgers, or did you grow fat separately?
Well, currently we grow fat separately. So we use the same stem cells and we use different conditions to drive them towards a fat cell instead of a muscle cell. And then you grow a fat tissue and later on you combine the pieces of fat tissue with the muscle fibers and you make a patty. For any processed meat, that's a perfectly valid solution. Again, if you want to make a steak, you need to find a way to co-culture them.
So what are the different conditions needed to push the same stem cell towards one musculoskeletal fate versus a fat cell fate?
Right. So for these stem cells, the muscle-derived stem cells, for them to turn into muscle cells, we actually starve them. So we take away all the proteins that are required to let them proliferate. So basically, we call that starving, although it's not essentially starving, but it's something similar. And then they stop proliferating and they start to fuse, they start to merge, because the muscle fiber is basically a merged number of cells. And that's the first step towards muscle differentiation. And then when they start to contract, they need to have anchor points so that they can develop tension. That's the muscle lineage. In order to make them fat cells very early on, you feed them fatty acids. The protocol to make fat cells has been described, but is not in itself compatible with food production. So we have changed that and looked very carefully at the process. Well, if we give them fatty acids, natural fatty acids, such as unsaturated fatty acids, or even some branched saturated fatty acids, they start to develop into fat cells and become a fat tissue.
So you deliver fatty acids to the stem cells while they're still dividing.
Right.
Okay.
Yes.
While you wait for a certain amount of cells to be produced for the muscle cells and then starve them.
Right. Exactly.
So, lastly, well, you've mentioned creating hemoglobin, or
myoglobin.
I'm sorry, myoglobin. Which is it similar to hemoglobin? Is it a molecule within red blood cells?
No, it's similar to hemoglobin in the sense that it is an oxygen carrier, like hemoglobin, and it turns red in the presence of oxygen and blue in the absence of oxygen. So in that sense, it's similar. It has the same heme iron group in it. And the iron basically binds to the oxygen, and the heme group captures the iron atom in a certain condition. So that part is the same. The globin part, the protein part of it is different. Hemoglobin has 4 big protein chains, and myoglobin has only 1. Okay,
so I imagine in live cattle, the oxygen and iron would be captured from the blood. Is that correct?
That's true. And that's not only in cattle, that's in every mammalian species. So the function of this myoglobin in the muscle cell, it's in the muscle cell, and it's also produced by the muscle. So there is no blood involved in that part. Has a different function. It has a function in transport of oxygen from the cell membrane to the mitochondria in the cell where the oxygen is needed. And it also serves as somewhat of a reservoir of oxygen in muscle cells. So it's a common confusion that in red meat there's actually not a lot of blood. The animals have been bled, and so most of the blood is gone. And the red meat really derives its color from the myoglobin and not the hemoglobin.
So to get the iron and oxygen into the cells, that's just part of the nutrients that are fed to the cells?
No, they produce you need to feed them iron, that's in the feed. Mm-hmm. But the myoglobin itself is made by the cells. So you feed them all the necessary building blocks, but then they make the myoglobin, by themselves. The reason why we had to optimize it is because if you culture cells under ambient oxygen conditions, they don't really form a lot of myoglobin. So what you have to do is you have to grow the cells under lower oxygen conditions so that they start to form this myoglobin.
So you talk a lot about getting sort of the right mouthfeel, the right texture. Do you have any experts to evaluate these things? Are there people with those kind of jobs, or are you guys just going on your carnivorous experiences?
Well, so far we have done the last. And but yes, at some point when we have scaled up production and have gone through regulatory approval, we will have a professional taste panel to judge tastes and to see where we have to improve or whether we are already fine.
How many hamburgers would you say that you have made to date?
Only 4, I guess.
Mm-hmm. And
because what we are doing right now is mostly at a scientific scale. We're not producing a whole lot of cells or hamburgers, but because everything can be done on a small scale.
Has the price gone down from the original investment?
Not yet, because that requires full scaling to, let's say, 25,000 liter bioreactors. But that's our calculation. If we go through that full scaling, then we will get down with the price. So far, we have gone down a little bit, but not enough.
Now, how large is 25,000 liters?
That's about half the size of an Olympic swimming pool.
That's a lot of space. And it would be,
right.
Like you said, because cells need anchorage points, it'd be shelf after shelf after shelf of cells. Is that correct?
Right. Well, actually, once we let them form fibers, they don't require a lot of space anymore, because those fibers are made of 1.5 million cells, and they take up only a very little space because they are really packed. The bigger issue with space and with medium and fluid and feed is while they are proliferating. That's actually the most intensive phase, where you require most resources and also most space. So it's really the proliferation phase where you multiply the cells, where all the resources go into. Once they form tissues, it's relatively easy and relatively resource efficient.
So besides the giant bioreactor, what are other aspects of an upscale in production? What would that look like?
Well, forming the tissues, again, is, that's something that doesn't require a lot of space and a lot of nutrients and a lot of materials, but it does require labor. So you need to do medium switches. You need to pipette the fibers in the exact right sort of form. So that requires right now a lot of labor that eventually has to be automated. So right now we are designing the equipment to automate that and to form those fiber structures in an automatic fashion, so that we don't have to handle them, and it doesn't really require labor. The biggest reason for doing this is, by the way, not to avoid labor, but really to avoid handling of the tissue by human hands.
So to maintain the sterility of the tissue.
Yeah, exactly. Yeah.
We'll be right back after this.
Science for the People is a weekly radio show and podcast that explores everyday life from a scientific perspective. We are a member of the Skeptic Network, a collection of blogs, podcasts, and video content focusing on science and critical thinking. To find out where Science for the People airs near you, or to listen to past episodes, check out our website at scienceforthepeople.ca. You'll also find links to support us at Patreon, to connect with us on Facebook and Twitter, and to subscribe to the podcast in iTunes. And now, back to the show.
Welcome back to Science for the People. Moving on to some issues with traditional meat production, what do you think are the most significant problems with the current livestock industry?
Well, in my mind, there are 3. One is that they use way too much resources, because animals are very inefficient, in particular cows, in converting their feed into food for us. Second, we know since some 10 years that there's a lot of greenhouse gas production associated with livestock, especially, again, with cows, because of the methane. So it has been estimated that between 15 and 20% of all our greenhouse gas emission on this planet can be attributed to livestock. And third, there are animal welfare issues, obviously, with intense herding and intense bioindustry that we all kind of know, but we tend to sort of ignore because we like our meat so much.
So you mentioned the greenhouse gas emissions, projected somewhere between 50 and 20% contribution to overall emissions. Now, this would include the production of feed for cattle, the methane, the transport of product to and from grocery stores, and waste removal, all of those factors, right?
Right, that's correct, yeah.
So, in a future, if the production of meat shifted towards cultured beef, some of these factors would still probably be relevant. You'd still have transport, but you would be able to eliminate methane production and production of feed and degradation of land. Is that correct?
Right. So studies that are admittedly sort of preliminary because we don't have the process complete yet show that you can reduce the amount of land that you need tremendously by about 90%, the amount of water by about 90%. Energy is a little bit debated. So some say you can reduce it by 60%. Some say it will stay the same. That is, I'm not completely familiar with those debates, but even if energy expenditure is the same, it will still not be associated with methane emission and with CO2. So it has to reduce greenhouse gas emission anyway. Energy, in the end, I think is not the biggest concern because we can use alternative kinds of energy that are not associated with greenhouse gas emission.
Can you see any drawbacks or caveats to lab-cultured beef then?
Well, I think the biggest caveat in my mind is basically that it becomes something industrial and cultured and no longer something that requires these cute animals. So it's a sort of more kind of an emotional, cultural thing that I can see as a disadvantage. On the other hand, it's progress, and we have gone through a number of those steps. So we'll get through this one also, and I think it will have the benefit of kind of relieving our conscience of having to kill animals for our food.
I would 100% eat all of that. I don't know. I know that
Thank you.
I would, I am not fully vegetarian, though I have been at certain points, and I have cut out certain meat products. But I dream of this day so that I can eat any meat I want, and I would not feel guilty about it, assuming, there's no FBS in there.
Right.
But I do, I guess that brings me to one of my next questions, which is about the public perception of eating this kind of beef and sort of the PR issues with this. How do you convince people to eat this? People that are less convinced than me?
Right. Well, there are a couple of things you can say about this. One is that we find it relatively easy to explain to people why we're doing this, right? All those reasons, everybody can relate to them and everybody can see those benefits. Then really you have to wonder what would hold people back from eating this. And I think one of the biggest things is just that it's new. Nobody knows exactly what it is yet, whether it's safe, whether it's long-term safe, that sort of thing. Because we have that with every new product, that there is a certain resistance and a certain reluctance to start eating that. On the other hand, once we have developed trust in these products, either through regulation or through somewhat a larger consumption scale, and we see, oh yes, this is a product that is safe and everybody seems to like it, then people are able to eat all sorts of things that they don't know exactly what it is or exactly how it's being made. We have, think in the United States of hot dogs. If I ask my audience, do you know what is in a hot dog? Most people say, well, I really don't want to know. Yeah. And I also don't want to know how it's being made. But yet it's eaten and it's very popular. Why? Because everybody knows it and because it's considered safe. So that requires time and obviously, it has to be a good product. It has to be safe. It has to be regulated. It has to be labeled. It has to be the taste has to be good, and it has to be relatively cheap, not much more expensive than regular meat, and preferably cheaper. So when those conditions are there, and give it a little bit of time, and it will sell itself. I'm pretty sure of that.
So it just takes a bit of time to get to that sort of ignorance is bliss state.
Right, exactly. And so what you need also is early adopters who are just adventurous enough and say, well, I trust this guy and I think this is a great idea, and let's start eating it. And those we have more than enough. It's also a regional thing. We did a survey in the Netherlands, where cross-sectional through the entire population, 15,000 people. And after a little bit of explanation what this is, we asked them, would you buy it if it was available in the supermarket? And 52% said yes, or probably yes, which is a big number of early adopters, which is an astonishingly big number of early adopters. Now that's the Netherlands, and it's for sure it's going to differ from region to region, but it has to start somewhere, and we're pretty sure it will start somewhere.
Now, I guess an analog for this is that at least in the U.S., plenty of people eat GMOs. It's not required to be labeled. I believe there's only one market that does label genetically modified or food with GMOs in it. So genetically modified organisms. So, and some people are very anti-GMOs, but a lot of people have gotten over it. So I imagine that could be something to look at when considering how people might adapt to something like this.
Right. And again, there we also see a lot of regional differences. In that same survey, we asked people, what would turn you away from this? And GMO is right up there.
Right.
So yes, in certain regions, GMO is kind of accepted, and I think here in Europe, a lot of people know that some of our foods are prepared in GMO-produced oil and that sort of thing, plant-based oils. But the combination of the two, for the moment, is still sort of killing.
So while we're on this topic and the distrust of GMOs, there are some really crazy advantages that could come from a diet based on just lab-cultured beef. So there's issues with, as you mentioned earlier, the sterility of the environments that these animals are slaughtered in, and the treatment and hormone use and antibiotic use, potential for potentially affecting the effectiveness of antibiotics in human medicine. Could you talk a bit more about the differences and whether any of these products that are used in factory farming would need to be used in an upscaled version of lab-cultured beef?
Right. So we have worked on eliminating antibiotics from the entire system, and we can do that. So we don't need antibiotics. We don't need hormones, at least not the steroid hormones. You still need some of these proteins that I mentioned that are typically in our blood that help cells grow. The product is sterile, so by definition, so it should have a longer shelf life in terms, at least, of its microbial content. It will still degrade because of the enzymatic degradation, so it will age the same way as regular meat will age. But yeah, in the production system, there are a couple of advantages in that you can eliminate components like antibiotics and like hormones.
Speaking of production, you talked earlier about automating these processes. Have you gotten much pushback from people about the, people employed in the livestock industry and people that would be put out of a job in this sort of economy.
Right. And I think it's a huge part of the economy, and a lot of people depend on that industry. So it's something that you have to be very sensitive to, I think. A big part of the industry, especially the processing industry, will not be affected because they will essentially use another raw material for their processes. So they will not be affected too much. But the ones that are affected a big deal are the farmers and the larger meat producers, the farming communities. So there are a couple of ways of looking at this. For me, a farmer is the ultimate entrepreneur. He just wants to extract value from his land, and if he can produce crop that can be used as feed for these cells instead of breeding and raising animals, as long as he can make money from his land, he will do that. I've seen examples in my neighborhood where pig farming is no longer profitable, and people move because of that to potatoes or to legumes or to wheat or whatever. And they will do that solely on the basis of economic reasons. But they will need some time to transition into that. And of course, they will have the time because this is not going to be an overnight sort of revolution.
But the meat companies probably won't be too happy with this kind of transition and might put up quite a fight.
Yes, they could. But what you see is that, and for, I guess, a couple of reasons that we can sort of speculate on, is that they actually become interested in this. So they Tyson has started investments in the vegetarian sphere. A lot of meat companies in Europe have invested in vegetable alternatives for meat. So they also see that there is a societal need for this, and that they need to adjust their business strategies towards alternatives for livestock meat proteins. So I think it's also it's going slow, but you see the beginning of interest from these companies, and they really start to invest in this space. So I think. And there are a couple of reasons. One is that the public kind of demands it, but the second is also that they realize that they cannot really produce enough to meet global demand in 2050. It just cannot be done.
Now, what are the projections on the demand in 2050?
Well, according to the FAO and the World Health Organization, it's the global demand for meat is going to increase by 70% until 2050, and we just don't have the resources to do that.
And it's hard enough for all of the food products imagined to be distributed within developed countries. But what do you know about access to meat in developing nations?
Well, it's basically a matter of, at least in China and India, it's mostly a matter of money. Meat is a very expensive protein product, and most of the people just don't have enough money to buy meat. That's why they are sort of involuntary vegetarians. That will change, and it is changing. So Chinese middle-class incomes will rise in numbers, and so will the same in India. And those people, the first thing they will do is strangely enough, they start to eat meat. That's where the 70% rise in meat consumption is coming from in the coming 35 years. It's not coming from the increase in world population.
And it's not coming specifically from the increase in population in China and India?
No, it's primarily increase in wealth.
Interesting. So in line with talking about how the world will be changing, hypothetically, with this kind of advance, You mentioned earlier that the goal is to get the amount of cattle or livestock, cattle and animals from, I believe, cattle, 1.5 billion to 30, what was the number you stated?
1.5 billion to, let's say, 30,000.
So what would the lives of these cattle look like?
It's basically a choice that we have. We can, at the very least, they will have much more space and they won't be so confined. So they can move around. If they have more space, that will not impinge on the economic viability. They can become older if we wish that, and if they're not sick, so that will be, for the few cows that are still there, would be a major change.
But we're not talking little samples of beef from these cows. These cows will ultimately be slaughtered for full musculoskeletal samples, correct?
That's one scenario, and certainly for, in a way, in my mind, a preferable scenario, because then you don't have the aging animals and you don't have the animals that are emitting methane all the time. Right. And also for some religious populations, that might be the preferred way. For instance, halal and kosher probably require the animals to be slaughtered for their stem cell harvest. So that's one scenario. But if we really would want to, we could keep the animals alive and just take small samples from them. Considering
how much yield of stem cells or muscle cells do you get from a small amount of muscle?
Well, from the small amount of muscle that we can take from a biopsy, we have estimated that we can make 10,000 kilos of meat.
10,000 kilos.
Right.
I'm trying to picture this in pounds because I don't have a reference point, but I can figure it out.
That's about 20,000 pounds.
20,000 pounds of beef.
Right.
Which
and
could
that's
feed how many people?
Well, considering that on average we eat, it depends a little bit on whether you are in the United States or Europe. Well, let's say if, a very modest amount of meat that you eat, 25 kilos per year, by one person, so that's 400 kilos. So 100 kilos would feed 4 people, and 10,000 would feed 400 people.
And that's from a sample of beef. What size?
It's basically less than a gram.
Wow, that's prolific. That is a large yield.
Right. So
obviously the livestock industry, if this kind of future happened, the situations or scenarios for animals would be much improved and a lot less animals would be slaughtered. But let's envision a sort of meat-free or animal-free cultured beef. Is there possibility for an immortalized stem cell line for musculoskeletal cells?
In theory, yes. You could use stem cells that divide forever, and that at some point, at will, you can let differentiate into muscle cells. In theory, that can be done. I'm not sure whether that would be a big added benefit that would just eliminate the last 30,000 animals, and you still want to keep some of those animals for biodiversity.
Right.
And I'm not sure that will be a great step forward, but in theory, it can be done.
Okay. So a couple more questions for you before we let you go. You mentioned a couple of things that you are being able to scale up production of the beef in your lab, but what are the next steps needed to get these burgers for the first time on the shelves?
Well, one obvious step is that we need to obtain regulatory approval, which might be different for the US than for Europe. In Europe, it's for sure going to be novel food. So that means that you have to prove that it is safe and that the production method is safe. That approval period takes about 18 months, and we have to document a lot of the stuff that we're doing. So that's a major step. And then really the scaling up to the 25,000 liter tank, which initially will be quite a big investment into filling those tanks. So it requires a big sort of startup fund.
So the scaling up of the tank, do you imagine that would need to happen simultaneously with the regulatory approval, or would this sort of what you're doing in the lab be okay to approve?
No. It will have to be in line with the regulatory approval. So we have to do that sort of simultaneously.
So you have to make that investment despite potentially not getting regulatory approval ultimately.
Right. Well, we are actually pretty confident that we will get regulatory approval. So we don't think it's a huge risk.
And at least in Europe, what do you think will be the labeling of these products in the marketplace?
I don't know. That's a kind of a political question, I guess. I think eventually, that's what I sort of foresee in 10, 15 years or maybe 20. It will probably be the reverse, that the livestock meat that is still available in small quantities will be labeled as such. And the rest will all be cultured. That's what I think will happen at some point, which you now see happening, for instance, with cultured salmon. It's not a complete analogy, but if you now buy a wild salmon, it's labeled as wild, and the rest is just salmon.
Yeah, that is interesting, and it's true. The labeling can also be very misleading, like in the U.S. at least, where we have all these images of farms and on these packaging, and chicken will say hormone-free, even though there is not allowed to be use of hormones in American chickens. So we'll be interested to see.
Right.
Yeah, gluten-free rice, all of that. So.
Yeah.
So I have one last question, and this is very silly and small, but I know that, raw meat needs to be refrigerated, but this meat is incubated not in a refrigerator, right? It's room temperature?
It's actually body temperature of the animals. So it's 38 degrees centigrade.
So at some point, does the burger need to be refrigerated?
Of course. So in order to keep the cells alive, you have to keep them at body temperature. At some point, you kill them, right? You kill the cells, you kill the hamburger, if you like. And then obviously after that, it's refrigerated. Otherwise, it will degrade pretty quickly.
Well, I do think I'd rather have a killed hamburger than a killed cow.
Right, exactly.
Well, thank you so much for being with us here today. It really is such a fascinating topic, and with such a large potential impact on the global food industry as we know it.
Right. It's a pleasure to work on this. Yeah.
Well, we look forward to seeing what comes next from you.
Okay. Well, we'll keep you posted.
If you're interested in learning more about Dr. Mark Post and cultured meat, navigate to culturedbeef.org. You can find more information and links to Mark's sites on the show notes for this episode, which you'll find on our website, scienceforthepeople.ca.
And now for something completely different. When we get back, we'll be hearing from astronomer Chris Crockett about the Cassini mission to Saturn and a brave little spacecraft's impending fiery doom.
Every week on Science for the People, we take the latest in scientific progress and relate it to people, our friends, our families, our communities, and our society. And we give researchers, authors, and journalists the time to talk in depth about what matters to them. If you love science but aren't satisfied with sound bites, join us again next week for Science for the People on your local radio station or anytime online at scienceforthepeople.ca.
Welcome back to Science for the People. I'm Bethany Brookshire, a science writer with Science News and Society for Science in the Public. And have you heard about Cassini? This intrepid little spacecraft has been heading towards Saturn, and starting next week, it will start taking daring dives into the rings surrounding the planet. Here to tell us more about what to expect is Chris Crockett, an astronomer and freelance science writer. Thanks for joining us, Chris.
Thanks for having me, Bethany.
So, first of all, can you tell us a little bit about the spacecraft? What is Cassini?
Cassini is a probe that has been orbiting Saturn since 2004. It's actually been in space for almost 20 years. And it's been orbiting Saturn for about 13 of those years, checking out the planet, checking out the rings, the many, many moons. One of the first things it did when it got there actually was drop a lander on the largest moon, Titan, which sent back some spectacular images of methane lakes and clouds on the moon. It's a really cool mission.
And who's driving this thing exactly? Who launched it and how does it work?
It's a joint mission between NASA and the European Space Agency.
How do you drive a spacecraft like this? Because I looked up Cassini and they mentioned it was running out of rocket fuel. Mm-hmm. So how does that work? Like, who drives it and what do they do with it to like make it turn around?
Well, I think it's still got enough fuel for now. Basically what they do is, they actually use the gravity of the moons a lot to redirect the spacecraft. One of the things they'll be doing over the next couple of weeks, and what they have been doing, is getting really close to, say, Titan. And to conserve fuel, they'll use the gravity to slingshot around and change course.
So it's like in The Martian when I think they miss him at one point and they have to slingshot around the planet.
Yeah, it kind of is, actually. It's really cool watching them try to figure out how to do this. They do some really crazy, clever maneuvers to move the spacecraft around the planet using just the gravity. It's actually part of how they got it out there, too, was they did multiple passes by Earth and Venus and Jupiter, each pass by a planet, picking up more and more speed, and getting it out there.
That's really neat. So it's been hanging around Saturn for a pretty long time. What kind of things has it taught us so far?
I think some of the coolest things have actually come from checking out the moons. Saturn has just got this amazing collection of moons. You have learned about Titan, the largest moon, which has seas and rivers of liquid methane flowing on the surface. It's actually a lot like Earth. It has storms, it has seasons, it has sand dunes and mountains and canyons. It's a very cool place. And then you've got a place like Enceladus, which is completely covered in ice. And one of the things that Cassini has taught us is that there is a global saltwater ocean, liquid ocean, sitting underneath that ice. And I've been able to figure that out because they've actually seen water geysers erupting from the south pole of the moon and shooting water off into space. And the Cassini's actually flown through those plumes a few times and basically tasted the spray and sampled the composition of the water.
Wow, it got really close.
It's gotten really close. I mean, it's for some of these moons, it has just buzzed them. I don't know the distance off the top of my head, but yeah, it gets in really, really close and sends back some amazing images when it does. But yeah, the spacecraft's actually been sprayed by a moon now.
I just love the idea of Titan, and people say, oh, it's Earth-like, it's got sand dunes and seasons, except for the fact that it's all methane.
Methane, yeah. It's Earth-like except the fact that it's minus 200 something below zero, and it's methane, and so, but I mean, these moons like Titan and Enceladus are a couple of places in the solar system where planetary scientists think there may actually be a chance of finding life.
I have to say, if there's life on Titan, it's probably very, very smelly life.
And should never ever light a match.
Definitely not. No.
There are no smokers on Titan.
Now, it's been buzzing these moons and sampling and finding out about, the underground oceans on Enceladus. So we know that next week something big is about to happen. NASA has a counter going down. What kind of actions are going to happen?
Well, Cassini's mission is coming to a close this year. And because it is, the spacecraft engineers are getting a little more daring with the spacecraft. So what they're actually going to do is they're going to swing by Titan on the 22nd and use Titan's gravity to slingshot around, and then a few days later actually dive between the planet and the rings. And that's going to be the first of about 22 orbits where it's going to, each time it comes around, it's going to buzz the planet and go. Sometimes it's going to come really close to the inner edge of the rings. Sometimes it's going to just graze the atmosphere. This is something they would never have done at any other point in the mission, because flying through the rings is, not a great idea with a really expensive spacecraft. But all bets are off now, so they're just going to see what happens. And actually, one of the cool things they're going to do, because they don't know if it's going to damage the spacecraft or not, and so in the first few passes, they're actually going to turn the spacecraft so the big bowl-shaped antenna is sticking out in front, and they're going to use it as a shield, basically like a snowplow. And as it goes through the rings, if the spacecraft gets pelted with anything, all the debris will hit the antenna first and won't damage the instruments. And the antenna can take a little bit of a beating and still work. So they'll do a few passes like that, and everything's holding up. They may actually turn the spacecraft around and send the instruments through first and see what they learn.
And what kind of information do scientists hope we're going to get?
Well, one of the things they're going to do is just getting that close to Saturn is going to probably show them a lot more details about the clouds and the winds moving in the planet. They're going to get some really up-close measurements of Saturn's magnetic field and its gravity, which can tell us something about what the interior of the planet is like. The interiors of these planets are still largely unknown. They're just big balls of gas from the outside. And so there's a lot we don't know what's going on inside. And I know one of the cool things they want to do, too, is actually try and measure the mass of the rings, which we don't know. We don't know actually how much stuff is in there. And they can do this because they can compare every time Cassini's flown outside the rings, they can compare like how the gravity, all that mass of Saturn and its rings kind of pulls in the spacecraft. Now when they fly inside the rings, they can see how the gravity affects it then. And by comparing how it's different outside the rings and inside the rings, they can figure out how much of that gravity was coming just from the rings itself. And that can tell us something about how the rings are made, how long they've been there. And these things are still debated, believe it or not.
And at the end date is September 15th.
September 15th, yeah.
What's going to happen then?
Oh, it's Cassini's going out big. It's actually going to crash into Saturn. It's just going to dive bomb the atmosphere, sciencing for as long as it can until the atmosphere just crushes it to death. So it's going to be, as it dives in, it's going to try and make its measurements for as long as possible, measuring the composition, things like temperature and pressure. And they'll see what we see. They don't know how long it'll last. But the reason they're doing it is actually really cool. It's because they don't want to risk crashing into any of those cool moons like Enceladus or Titan. There is a chance, however remote, that there's some sort of life swimming in the seas of Enceladus. And the engineers don't want to risk contaminating that life. The bacteria, there may still be Earth bacteria hanging out on Cassini somewhere. And so just to protect those moons and to protect any future investigations, they're going to dispose of it in Saturn's atmosphere.
Yeah, because I remember the original idea was just to kind of abandon it in the kind of gravitational pull of Saturn and just kind of like leave it near Saturn. Mm-hmm. But that's interesting. Did they change did they put it on the collision course once they realized there was a salty ocean on Enceladus?
Yeah, all these things they've learned about Enceladus and Titan, is I think what led them to change their minds. Other spacecraft have done the same things, actually. The Galileo spacecraft at Jupiter also ended its mission diving into Jupiter, and the Juno spacecraft that's there now is going to do the exact same thing. And it's all to protect the moons and protect any life there. Is
there anything that we should particularly watch out for in, scientific news coming out from this? Well, I think some of these I think that the highlights are going to be some of the just fantastic images that are going to come out of it. To me, that's always been one of the big highlights of Cassini is just the really cool pictures. And so, you've already seen, actually, if you've been following it in the past couple months, some amazing up-close images of some of the weird moons that orbit around Saturn. And so we're going to probably see some really up-close things and some cool things about the rings themselves, what they're made of, some never-before-seen angles looking from inside the rings out. Who knows? That's the great thing about this thing is, we don't know what they're going to discover. That's kind of the fun part. So, Well, thank you so much, Chris. I don't know about you, but I'm definitely going to be keeping an eye out.
Oh, absolutely. Me too.
If you'd like to learn more about Cassini, we've linked to the NASA site where you can watch the nosedive in real time at scienceforthepeople.ca. There you'll also find links to Twitter, Facebook, and iTunes, where you can listen to past episodes, subscribe to the show, or leave us a review. You can also find our Patreon page, where you can toss a monthly tip in the hat for our intrepid podcasting gang. Thanks for listening, and we'll see you next week on Science for the People.
Science for the People is produced by Rochelle Saunders and edited by Ryan Bromsgrove. Helen Quivalon is our publishing liaison. We get research help from Josh Witten and consulting support from Desiree Schell. Our frequently seen guest hosts are Marion Kilgour, Anika Hazra, and Jessie Yaros. Our theme song is called Binary Consequence, and it was written and recorded by Fractal Pattern. Science for the People is entirely listener-supported. You can find us on Patreon, where you can support us with monthly donations in any amount, or you can send us a one-time donation in any amount via the donate page of our website. Science for the People is created in partnership with the Skeptic Network. a collection of blogs, podcasts, and video content focusing on the intersection of science, popular culture, politics, and social justice. You can find out more about Skepchick at skepchick.org. The show is hosted by science news writer Bethany Brookshire and me, Rochelle Saunders.